Okay, so if you remember, yesterday we defined the problem of finding a special filter, which is called beamformer, and we found what is called classical beamformer. So the impulse response H of the beamformer, which is a discrete linear time invariant filter, an FIR filter. H is proportional to A. So it means that the classical beamformer is nothing but a meshed filter. And then we derive the angular spatial power spectral density estimate. So an estimate of the power spectral density as a function of the direction arrival theta by using the classical beamformer. And this was basically the solution. So you can express the spatial PSD estimate by using the classical beamformer either in this term as a function of the sample covariance matrix estimate, or if you make it explicit the sample covariance matrix estimate, and you manipulate, you change a bit the expression, you manipulate a bit the expression, you come up with this expression here. So Y Hermitian of NA basically is the output of the classical beamformer. The modulo square is the power, and then you divide by the number of sensors. And then you calculate this quantity for any snapshot, for any temporal snapshot, and then you calculate the arithmetic mean, the average. Now, if the array is EULA, so it's a uniform linear array, this relationship, which is general, becomes a discrete time Fourier transform, because the elements of this array response A becomes a complex exponential at the spatial frequency Fs, which depends on the directional arrival. Fs, if you remember, is d over lambda sine of theta, where theta is the directional arrival. So in the case where the array is a EULA array, uniform linear array, basically the estimate of the power spectral density as a function of the angle obtained by using the classical beamformer is just the average periodogram, because what is in parentheses is the classical periodogram, FFT of the data modulo square divided by the data length. And then you average in this case over time. So this is what, I don't know if you are familiar with classical techniques for power spectral density. This is what has been called in power spectral density estimate, has been called average periodogram, or sometimes it is also called Bartlett method. So the property of this method to estimate the spatial power spectral density are exactly the same of the Bartlett method. So I don't know exactly what is your background, but if you have studied power spectral density estimate, you can immediately understand the close relationship. And so how do we estimate the directional arrival of the sources or of the target? We get this estimate of the spatial power spectral density, and then we search for the location of the K largest peak. So from the location of the K largest peak, we get the normalized spatial frequencies, and then by inverting this relationship, we get an estimate of the direction of arrival of the sources, of the K sources. You should notice that this is a non-linear mapping between the direction of arrival, theta, and the normalized spatial frequency f. And the fact that this mapping is non-linear, as you will see, creates some problems. We will see later. Okay, now, in general, we have multiple sources. So K, capital K can be greater than 1. So we will have multiple peaks in the estimate of the spatial power spectral density. So the question is, what is the resolution of the classical beamformer? So remember, the classical beamformer is the equivalent of the Bartlett method. The Bartlett method is the average periodogram. Averaging has the goal to reduce the variance in the estimate, but the resolution of periodogram, I hope you remember, is the reciprocal of the sample size. So in the estimate of two frequencies, you can separate them, you can estimate separately them if the distance between the two frequencies in the digital domain, so digital frequency, is greater than the reciprocal of the data size. So if you apply this well-known result, so this is what is called in power spectral density estimation Rayleigh resolution or Rayleigh limit. So if the array is Euler, you can apply directly this result to classical beamforming. So you can separate two sources coming from different angles, so from different spatial frequencies, if the distance, so if the difference between these two spatial frequencies, so fsi and fsk, is greater than the reciprocal of the sample size. And in this case, the sample size is the number of sensors. So should be greater than 1 over n. So this is the relationship that should be satisfied in order to guarantee that all the sources can be separated, can be resolved, and their direction arrival separately estimated. Now, if you remember the expression of the spatial frequency, it is d over lambda sine of the direction arrival. So if you make the replacement, you get this other relationship. So you bring outside d over lambda, so you get d over lambda that multiplies the inferior, the minimum of the modulo of the difference of the sign, and this should be greater than 1 over n. Now, if you bring d over lambda on the right-hand side, the relationship becomes the following. The inf of the modulo of sine theta I minus sine theta k should be greater than lambda divided by the product between m and d. Now, lambda is the wavelength. M times d, if the array is Euler, is exactly the array length, or the array aperture. Now, the wavelength divided by the array length is approximately the array beam width, so the width of the main lobe. And so, in other words, the relationship becomes the following. So in other words, and this is very intuitive, you can separate two sources coming from two different angles only if the difference between the two direction arrival is at least greater than the array beam width. So the width of the main lobe of the beam pattern. We will see some numerical example, obviously, but this is a very intuitive result. Okay, and now we want to analyze the performance of the classical beamformer. Remember, only if the array is Euler, the inner product between the data vector and the array response is the discrete Fourier transform of the data. So only if the array is Euler, you can calculate the output of the beamformer by using the FFT. So a good thing of a Euler array is the fact that the output can be efficiently calculated by using the FFT. If the array is not Euler, you can't use the FFT, and so the computational complexity is greater. So when we talk about FFT-based beamforming, it refers to Euler array because it is possible to use FFT only for Euler array. Now, let's investigate the property of a Euler array, both in the case where there is only one source and there are multiple sources, so K is greater than 1. And I want to show you that if there is only one source, the method is consistent. And what I mean when I say consistent, I mean that when this number of snapshots n tends to infinity, the estimate tends to the true value. So the estimate converges to the true value. This is true only, this happens only if K is equal to 1. So this method to estimate the direction arrival is not consistent if we are in presence of multiple sources. Now, how do we prove this? How do we show this important fact? Okay, we start, first let's assume that K is equal to 1. Now, we know that the sample covariance matrix, as any sample estimator, is consistent. So when the number of samples, so the number of snapshots n tends to infinity, the sample covariance matrix tends to the true partial covariance matrix because the average mean tends to the statistical expectation. This is called sometimes large numbers law. And it's a property of all sample estimators. Okay, so it means that the estimate of the spatial power spectral density, so when I talk about estimate, I put the at on the symbol. So this is the estimate tends to the true spatial power spectral density. So the same quantity without the at. And the true power spectral density at the output of the classical beamformer, if you remember, we have calculated, it is given by this expression here, 1 over m A Hermitian RYA. Now, if there is only one source, what is the structure of the correlation matrix or covariance matrix? It's the correlation matrix of the signal. There is only one signal. So the the covariance matrix of the useful signal is the power of the signal that multiplies A Hermitian, and theta t is the direction arrival of this signal. So remember, point-like target, point-like signal, point-like source, sorry. It implies that the covariance matrix has rank 1. So this matrix A Hermitian has rank 1, plus the full rank covariance matrix of the noise. And let's assume that the noise is white. So the covariance matrix is sigma W square I. So if this is the structure of the spatial covariance matrix, what is the expression of the spatial power spectral density? We just have to make a replacement. So in place of Ry, we put this expression here. And you make this replacement, we get Ps over M. Then we have A Hermitian of theta. Remember, theta is what? Is the angle at which we calculate the spatial power spectral density. And theta t is the direction arrival of the single target or the single source which is present in the data. So we are estimating the spatial power spectral density from data where only one target is present, and this target is observed in the presence of additive white noise. So we make the replacement. The product of these two terms is equal to the conjugate of these other two terms. So the first term can be written as modulo square of A Hermitian of theta, A theta target, modulo square. A Hermitian of theta, A of theta is the energy of A, and the energy of A, because each element of this vector has modulo equal to 1, the energy is m, because it is 1 plus 1 plus 1 plus 1 m times. So this is equal to m, you divide by m, so you get plus sigma w squared. Plus sigma w squared. Now, if the array is Euler, so let's calculate this quantity here if the array is Euler. So if the array is Euler, the array response is just a complex exponential. And in place of Fs, I put explicitly d over lambda synthetic. So when you calculate the inner product between A Hermitian and A, what you get is the summation of, so the inner product as a result gives a scalar, and the scalar is the first term of this vector multiplied by the first term of the second vector plus the product of the second terms and so on. So you have the summation for m that goes from 0 to m minus 1, and then you have the product of the two terms, but they have the same structure. So this is what you get. Now the problem is to find the closure of this summation. You may remember that this is just a geometric series truncated. So we know what is the result of this geometric series. So it's 1 minus this quantity here calculated in m divided by 1 minus this quantity here calculated in m equal to 1. So you have this ratio modulo square, and then you divide by m. Now, we want to express this term by using the sinc function. Remember, sinc of x is what? Is the sine of pi x divided pi x. So it's a well-known function in signal theory. Now, to express everything as a function of the sinc function, the first step is to obtain the difference of these two exponential. And to obtain this, we have to put in evidence e to minus j half of this angle, half of this. So without the 2. And the same at the denominator. So you put in evidence at the numerator this term. At the denominator, you put in evidence this term. And now you can recognize that you can express the numerator by using a sign, because you apply the Euler relationship, and you do the same at the denominator. So it's the ratio of two sine. And then, if you remember the definition of sinc, you can express this as the ratio of two sinc functions. So the difference in the argument is that the numerator, you have this term n that comes from here, So at the end is the ratio of these two sinc functions. So obviously this signal is periodic. And then you have modulo square multiplied by m. So if you make the replacement, you come up with this expression of the spatial power spectral density. So you have this term here, but this term here is nothing but what we define the array beam pattern. Actually, to be precise, because there is modulo square, this is called array power beam pattern. So without the square, it is what we define to be the array beam pattern, which is, remember, a sort of Fourier transform of the array response. So this is the array beam pattern, modulo square, and then you multiply by the energy of the signal, because PS is the power, M is the length. So this product here is the energy of the signal, plus the noise, and because the noise is white, so the covariance matrix is proportional to the identity matrix, it means that the power spectral density is constant in angle. So basically, the level of the power of the noise is uniform in angle. So we have the same noise power from all the angle. So when the noise samples are spatially uncorrelated, it means that the power spectral density of the noise is uniform in angle. So is uniformly distributed with respect to angle. So we don't have more power of noise from some specific direction, but the power is constant from any direction. So this is the meaning of white, a spatially white noise. Okay, so remember, we already defined this. So this is the nth snapshot. HB is the classical beamformer. So it's the impulse response of the classical beamformer. And the classical beamformer is a matched filter. So HB is 1 divided by m that multiplies the array response. So HB is proportional to the array response. So if you want to point the beam in direction theta, you have to build a filter, a spatial filter with impulse response matched, so proportional to the array response calculated at the pointing angle theta. Now, if in your data you have a target, you have a signal coming from direction theta t, and so the signal is A theta t that multiplies S of n, so it's the signal generated by the source or the signal reflected back by the target. The output is the generated signal that multiplies this term here. And this term here is the transfer function of the spatial filter, which is called beam pattern. And so the modulo of this quantity is what we call beam pattern, and the modulo square is the power beam pattern. If the array is Euler, the power beam pattern is the modulo square of this, the ratio of these two sinc functions. Now the question is, if there is only one target, is the method consistent? The answer is yes, because how do we estimate the directional arrival? We search for the peak in the estimated spatial power spectral density. And the estimated power spectral density is proportional to this term here, to the power beam pattern. It's proportional to this, it's proportional to the power beam pattern. And this term here has a peak exactly at theta equal to the directional arrival of the signal. And so the estimate, which is the position of the peak, when n tends to infinity, coincides exactly with the true value theta t. And these are some numerical examples. These are some numerical examples, for example, assuming d over lambda 0.5. Remember, this is the maximum value that d over lambda can assume if we want to respect the Shannon theorem. So if you want to avoid aliasing in the spatial domain. Then the number of sensors is 16, and there is a signal coming from 0 degrees. So if you plot the beam pattern, and remember, when n goes to infinity, the estimate of the spatial power spectral density is proportional to the power beam pattern, as a peak exactly at 0 degrees. So we have a main lobe with a peak exactly at the true directional arrival. The width of the main lobe, we will calculate exactly. But if you calculate in frequency, it's on the order of the reciprocal of the number of sensors. So it's inversely proportional to the array aperture. But the problem is that you have also side lobes. And the problem of side lobes, as we will see, is that the presence of side lobes can mask other targets that are weaker than this target, and so can be masked by the side lobe of the strong target. So in other words, weak targets can be masked, so covered by the side lobes of strong targets. So we would like the side lobes to be as small as possible. Now, if you use a Euler array, the first side lobe is at minus 13 dB, and this is considered a too high value. So this can be a problem. And you will see there are techniques to lower this side lobe, which is too high. Minus 13 dB is considered to be too high. So there is a large risk of masking with targets. Now, if the target is coming from a different angle, for example, 20 degrees, you can see that the method is still consistent, because now the beam pattern has a peak exactly at 20 dB. But it's not just a shift of the previous beam pattern. This is due to the nonlinear mapping between the frequency Fs and the angle of arrival theta. So if you plot the beam pattern as a function of the normalized partial frequency, it would be just a shift. But if you plot as a function of theta, because of this nonlinear mapping, it is not just a shift, but there is a distortion. And what happens is that when theta t is different from 0, and the main lobe changes, but also the side lobes. So if theta d is larger, for example, 80 degrees, you see that the width of the main lobe increases. So the larger is theta t, and the larger is the main lobe. So the worse is the resolution. So things gets worse as soon as the directional arrival of the target deviates from the normal to the array. So the best case, the most favorable case, is when the target comes from the normal of the array, so 0 azimuth. When the directional arrival increases, so it goes towards 90, or decreases, so it goes towards minus 90, things gets worse. And you can see clearly if you compare these three figures. Theta t, 0 degrees, 20 degrees, and the main lobe, you can see, increases. Close to 90, the situation is pretty bad. So 90 is the situation that is called end fire. Now, what happens if you don't respect the Nyquist criterion? You have aliasing. So for example, if d over lambda is equal to 2, you have aliasing. How, I mean, what is the effect of special aliasing? It's different. The effect is the following, that you don't have anymore a single peak in the interval minus 90, 90, but you have multiple peaks. So this introduces ambiguity. So because if you have a signal, you don't know if it comes from 0 dB, from this other angle, or from this other angle. So you are no more able to estimate unambiguously the directional arrival of your target. And so, I mean, these additional lobes that are creating because we don't respect the Nyquist criterion, these are called grating lobes. So if you want to avoid the insurgence of grating lobes, we should respect the Nyquist criterion. That's why typically all the Euler array are built with the maximum possible ratio d over lambda, which is 0.5. So you don't go beyond that because of the grating lobes. You want to avoid the insurgence of grating lobes. So we choose the maximum value. Why the maximum? Because if d is the maximum possible, you have the maximum aperture. And the maximum aperture means the best possible resolution. So the narrower main lobe, but maximum take into account of the Nyquist criterion, and the maximum of d over lambda is 0.5. So in summary, we can observe two important facts. When the direction arrival of the source theta t increases, the beam increases. And so the resolution gets worse. And remember, the resolution is the ability to separate different sources. So signals coming from different direction arrival. If d over lambda is greater than 0.5, we have spatial aliasing. And you see this because you start to see grating lobes in the beam pattern. And the presence of grating lobes has the effect that we cannot estimate anymore the source direction arrival unambiguously. Because there are multiple angles, multiple peaks, and so you don't know which one is the right one. Okay, now let's calculate the beam width exactly in angle. So now, if we point the beam in the direction arrival of the signal, so if theta is exactly equal to theta t, the power beam pattern is equal to 1. So if you replace here, you put theta equal to theta t, this is 0, this is 0, so you get 1. Sinc of 0 is equal to 1. Where are located the nulls of the beam pattern? So are those values of theta for which the beam pattern is equal to 0. Now, because at the numerator we have a sinc function, when the sinc function is equal to 0, when the argument of the sinc is an integer, positive or negative, different from 0. So we set the argument of the sinc function at the numerator equal to an integer. So from this relationship, we find for each theta t, we find the values of theta for which we have the nulls. Now, so d times m, remember, is the array aperture. Now, let's calculate the closest null. So for, this quantity equal to -1. And let's call the distance from the peak theta BW. So theta BW is what is called basically the band, the beam width from the peak to the first null. So in place of theta, we put theta t minus theta BW, so the beam width of the first null, and this difference should be equal to lambda divided by d times m, which is the array aperture. So from this relationship, we find the beam width theta BW. So we bring this term on the left, we bring this term on the right, we calculate the arc sine, and we isolate theta BW, theta bandwidth. And so this is the exact expression of the beam width from the maximum to the first null as a function of theta t. So it depends on the array aperture, it depends on the central frequency, because lambda is inversely proportional to the central frequency of the narrowband signal. But the beam width, as we observed before, depends also on theta t. So when the signal is coming from different direction, the resolution changes. Now, the most favorable case is when the signal is coming from the normal, so zero azimuth. So theta t equal to 0, sine of theta t is equal to 0, and so you get the beam width is arc sine of lambda divided by the r. So you can see that when the array aperture increases, the array aperture is d times m, the beam width decreases, so the resolution gets better. Now, to increase the array aperture, you have two options. Either you increase d, but remember, d cannot be greater than lambda over 2. Or you increase m, so you build an array with more sensors. But when you add sensor, you add all the circuitry, the analog to digital conversion, the antenna, and so on. I mean, so it has a cost. So you can improve the resolution only by spending more money in the hardware. So the array aperture, MD, is a very important fact in determining the resolution of the beamformer. And the larger is the array aperture, and the better the resolution is. Then if you fix M and you analyze as a function of d over lambda, the beam width is inversely proportional to d over lambda. So as I said, d over lambda should be the greatest possible, but we cannot make d over lambda greater than 0.5. Otherwise, we have the aliasing, we have the grating lobes. So d over lambda equals 0.5 is the highest distance, normalized distance that we can have if we don't want grating lobes. Now this EULA with d over lambda equals 0.5 sometimes is called standard EULA. So the resolution depends on the width of the main lobe, and we have understood that it depends, depends on the geometry of the array, but roughly speaking, it depends on the aperture of the array. It's inversely proportional to the aperture. The larger the aperture and the better the resolution. But also the presence of side lobes is important. So in any beam pattern, you have side lobes. And unfortunately, the side lobe can mask weak targets. So it's important to have the side lobes significantly low. I comment this and then we make the first break. Now, this relationship here is exact. But if M is large enough, it can be shown that that relationship can be approximated by this relationship. So this is an approximation that is accurate only for large M. So for large M, you see that the beam width is inversely proportional to lambda divided by the ray aperture, as we already commented. But then you have this cosine of the source direction arrival at the denominator. And so what happens? It happens that the closer is the DOA theta t to plus or minus 90 degrees, so when the direction arrival of the source approaches end fire, cosine of theta gets smaller and smaller, and because it is at the denominator, the beamwidth gets larger and larger. And so when we deviate from the normal, the resolution gets worse and worse. So now we make the first break. After the break, I will show you how it is possible to improve the resolution given the number of sensors that are available. So for fixed M, how we can improve the resolution by increasing the array aperture without increasing the number of sensors and without causing the presence of grating lobes. In order to achieve this very important result, we should leave the architecture called ULA, Uniform Linear Array. So, and we should use linear arrays, but non-uniform. Obviously, what is the price to be paid if you use non-uniform linear array and ULA? The price to be paid is that we cannot calculate anymore efficiently the output of the beamformer by using the FFT. So the computational complexity increases. So always, I mean, it's always a trade-off. So you cannot improve in any direction. If you want to improve in some direction, you have always to pay a price. And we will discuss this in the next hour. Okay, so let's have 15 minutes break. Okay.
Okay, sir. Thank you, sir. We can start the lecture now, sir.
Okay. So we have understood that if we use a Euler array, uniform linear array, which has a clear advantage in terms of computational complexity because it allows us to use the fast Fourier transform, which is efficient. The only possible way to improve the resolution, so to increase the array aperture, is to increase the number of elements. So in other words, we have to increase the cost of the hardware. Now, people started to think about how to avoid this. So how can we improve the aperture without increasing the number of elements, so without increasing the cost of the hardware, but still avoiding the presence of grating lobes. So we cannot just increase the distance, because at some point we have the grating lobes. So the idea was to use non-Euler array, non-uniform linear array. So linear, but not uniform. These arrays sometimes are called thinned, sometimes are called sparse in general. And then depending on the particular architecture, you can find different names. The most important, the first one that was proposed was the so-called minimum redundancy array, MRA. And then another quite well-known architecture is called nested array. Another pretty important is called minimum hole array, and another one, coprime array. I will not enter in the details, mostly for lack of time, of this different architecture. I just want to show you. I just want to show you how we can achieve the goal. For example, by using the minimum redundancy array, just to make clear the idea behind. Then, if you are interested, there are many papers and tutorials on sparse array. Okay, so let's consider the minimum redundancy array. What does it mean? It means, it means the following. So if you have a Euler array, for example, this Euler with 7, you can see that the distances between elements are d, 2d, 3d, and the largest distance between the first and the last is m minus 1 times d, okay? But there are only one couple with distance m minus 1d. But for example, there are different couples with distance d. So you have the couple first element, second element, but you have also second, third, but you have also third, fourth, and so on. Now, the idea of minimum redundancy array is to build an array where you have all the distances of the Euler, but with zero redundancy. So only one couple has that particular distance. So for example, if you consider this array non-Euler composed by 4 sensors. So you have a couple with distance d. Then you have, so the first and the second. Then you have a couple with distance 2d, which is the third and the fourth. Then you have another couple with distance 3d, so the second and the third. Then you have two couple with distance 4d, which is the first and the third. And then you have a couple with distance 5d, the second and the fourth one. And finally, a couple with distance 6d, which is the largest, the first and the fourth. So you can see that we have the minimum redundancy because we have only one, all the distances are present. All the distances that are also in the EULA with the same aperture are present. But are present, each distance are basically provided by just one couple. Now, a perfect minimum redundancy array actually does not exist if m is greater than 4. So if you want to have a larger sparse array with this principle, you have to accept either that some distances are not present or that some distances are provided by more than one couple. But, okay, now I want to compare these two arrays. So you can observe the EULA and the M array, they have the same aperture, but in the M array, you obtain the same aperture with less sensors, so less cost of the hardware. Now, if you calculate the beam pattern of the M array, the beam pattern is very simple. 1 divided the number of sensors squared, and then you have to calculate the array response. The element, obviously this vector is 4-dimensional. So how do you obtain this 4-dimensional vector? You just remove some of the, so you take the EULA array response, you remove the third element, the fourth element, the sixth element, and you remain with the 4-dimensional vector, and then you calculate the inner product of this 4-dimensional vector. So you get this summation, but only for m equals 0, 1, 4, 6. So 0, 1, 4, 6. Now, if you compare the two beam patterns, this is the typical result. So in blue, we have the EULA with 7 sensors. So you get some resolution. Remember, the resolution depends on the width of the main lobe. And then you have the side lobes. Then you have the minimum redundancy array with the same aperture. And you can see that the resolution is more or less the same. Actually, slightly better, but I mean, more or less the same. But the price to be paid is the side lobes. So when you remove these 3 elements, okay, the aperture is the same, so the resolution is the same, but the problem is that the side lobe gets higher. In green, you can see the EULA with the same number of sensor of the M array. Obviously, the side lobe are worse than the blue one, but are better than the red, but the resolution is much worse. because the aperture is smaller. So
Sir, just one query, if I'm allowed to ask.
yes, yes.
Here we can see that the beam widths are more or less same
Yeah.
for the minimum redundancy and the EULA. What about the directivity of the array?
Sorry, what? Repeat the question.
What about the directivity of the array? Will it be same or is it slightly lower because the side lobes are higher in case of minimum redundancy array?
Yeah, I mean the problem are the side lobe. So
Yes, so the directivity also goes down compared to a EULA.
no, they don't goes down, they go up. When you remove some sensors, the side lobes go up.
Yeah, and the directivity of the array?
I don't understand. Can you repeat more slowly? Sorry.
The gain or the directivity of the array.
But the gain is more or less the same.
Okay, so the gain is the same, only the side lobes go up and the beam widths are same. Is that correct, sir?
Uh, this is the beam pattern. So don't confuse the power spectral density with the beam pattern because there is a normalization term.
Yeah,
To get here, you have to multiply by the energy. The
yeah,
beam pattern is normalized in such a way in the maximum the value is 1, so 0 dB.
yeah. So in other words, the normalization factor is probably different for EULA and the MRA beam patterns.
These are the three beam patterns, and in the maximum, the value is 1 for the three of them. But by definition, by construction.
Okay,
So, I mean, it's not important the value in the maximum that by construction is 1. What you have observed is that you have when you look at beam pattern to understand if the array is good or not, you have to look at mostly, roughly speaking, two things: the beam width of the main lobe and the level of side lobes. It's clear that you cannot improve both. It's always a trade-off. And if you use a sparse array, you have some degrees of freedom to choose the trade-off that is good for you. So in other words, by not using a uniform linear array, you can sacrifice a bit side lobe, but you can achieve the same resolution because you maintain constant aperture with less sensors, so less cost of the hardware. Now, MRA is not the best option, but it was the first kind of sparse array that was proposed 30 years ago. So I use an MRA here because I mean, it's very clear the concept. And this is the message that I want to pass. So if you use sparse array, you can achieve the same resolution because you keep constant the aperture with less sensors. At the price of what? Side lobes. Then there are other architecture that have a better trade-off that allow to control better the side lobes. Okay, so I mean, the way that you build the sparse array using the minimum redundancy concept is not necessarily the best approach to keep low the side lobe. So there are other methods that tells you, mostly they use optimization method that allow you to decide which sensor remove from the EULA in order to maintain the side lobe below a certain level. So it's an array design problem that can be solved by using optimization method. But I just wanted to explain the concept. This is
Okay.
not the best possible sparse array. There are many other structures with different properties, with different characteristics. Definitely, some of them are better than MRA. But the idea is this one. So I just wanted to consider the simplest possible see. So this is the simplest possible example to describe the concept. So
Okay,
to
then. Thank you.
understand
Yeah.
the trade-off, there is a trade-off here, and yeah, what is important to understand is that it's always a trade-off. So you have to pay something. If you achieve the same resolution with less sensors, no way you have to pay something. And what you have to pay is in terms of side lobes. Then, depending on the particular architecture that you choose, you can find the trade-off that is the best for you. But this depends on the application. I mean, there is no a gold rule. I mean, what is the best trade-off changes from one application to the other. Okay, did I answer your question?
Yes, sir. That's clear.
Okay, now I want to show that the classical beamformer is a non-consistent method for DOI estimate if we are in presence of multiple sources. You will find I will describe the derivation of this result, but at the end the result is pretty intuitive and you can understand very well intuitively when I will show you numerical results, okay? But let's see how we can prove that the method is not consistent. What does it mean that it is not consistent? It means that if you have capital K sources, when n goes to infinity, not necessarily the K peaks are at the true direction arrival. So why? Okay, let's start from the array model. So if we have K sources, A, the steering matrix, you remember, is an M by K matrix, and each column is the array response calculated at the direction arrival of the K source. Okay, so these are the capital K direction arrival. This is the relationship between the spatial frequency and the direction arrival. So when n goes to infinity, the sample covariance matrix tends to the true covariance matrix, which is this one. Now, again, let's assume that the noise is spatially wide. So the spatial covariance matrix is the power of the noise multiplied by the n by n identity matrix. RS is the spatial correlation matrix of the sources. So it tells you at the same time how much the signals generated by different sources or reflected back by different targets are correlated. So it's a K by K square matrix. So again, we start from the spatial PSD that is obtained by using the classical beamformer, and we make this replacement here. So you make the replacement, so you get the signal term plus the noise term. If the noise is wide, the noise contribution is always a constant term. It's a constant level, and this level is equal to the noise power. Then we have the signal. Now, to understand how this term can be expressed, let's write explicitly. Now, let's calculate A and median times A. So it's A and median, A and median, A and median. Then we have RS. And then we have the Hermitian of this matrix here. So the Hermitian of this is the Hermitian of this term here. So you have A Hermitian theta 1, A theta. And then instead of having one after the other horizontally, you have one after the other vertically. Now, let's assume that the different sources are uncorrelated. So basically the signal is generated by different sources. So there is no reason why different sources should generate correlated signal. The correlation typically shows up when we have multipath effect. So if they are uncorrelated, it means that this matrix is diagonal, and on the main diagonal you have the powers of the various sources. Yeah.
Ok, no, che qui sono su, grazie mille.
Okay. So if this matrix is diagonal, when you calculate this product, this matrix times RS times this matrix, basically what you get is this term multiplied by P1 multiplied by this plus this term here multiplied by P2 multiplied by the second term and so on. So you have a summation for K that goes from 1 to capital K, this term, Pk, and then it's Hermitian, plus the noise contribution. So this term that multiplies this term is the modulo square of the first, because this is the Hermitian of this. And because they are scalar, it means that they are one the conjugate of the other. So you can write finally the spatial power spectral density as the sum of these different terms. So remember, when K is equal to 1, we have only one term. When we have multiple sources, you have the sum of different contribution. So why this introduces a bias? Because these different terms, if they are not well separated, what happens is that the presence of side lobe has the effect to change the position of the peak of the other terms. There is a mutual interference, and when you sum, the strongest source, so the one with the largest power, basically influences the position of the peak of the weak source. And this is true especially if some sources are close in space and they have different powers. And this is due to the presence of side lobes. So they are the side lobes that introduce a bias in the estimate. And so the method is not consistent if we have multiple sources. Remember, we assume that the sources are uncorrelated. But if they are correlated, the bias is even larger because you have additional terms, and this additional term in the summation introduces additional bias. And remember, typically the sources are correlated in the presence of multipath, because you receive from two different angles two signals, but these two signals have been generated by the same source, so they can be correlated. Now, if the array is Euler, for example, each term in that summation has this structure here. And so you can express the spatial power spectral density as the sum of this sinc function, each one weighted by the power multiplied by the number of sensors. So this is the energy of the k source. So this interaction can be evident if you look at some numerical example. So this is the true spatial power spectral density obtained by the classical beamformer. Here we assume that the noise power is 0, but I mean, it does not change the shape because it's just a constant term. There are 3 sources. The array is Euler. D over lambda is 0.5, 15 sensors, and the 3 sources have different powers: P1 0.1, P2 1, P3 0.25. So in dB, minus 10 dB, 0 dB, minus 6 dB. And the direction arrival are minus 30, 0, and 60. So this is what you see. Now, if the sources are space, you can see that the 3 peaks are really equal or very, very close to the true one. So there is no significant bias, but this is because the sources are far spaced. Now, if the distance between, for example, source 1 and source 2 is smaller, because source 1 is weaker than source 2, minus 10 dB weaker, you can see that now, because of the side lobes of the stronger source, which is source 2, the peak, this peak is not in the true value, which is minus 10 dB. So minus 10 dB is here, the red vertical line. But the position of the peak is not in minus 10 dB. So there is a bias that is generated by the interaction between the main lobe of the weak source with the side lobe of the stronger source. So this is the reason why, in general, in the presence of multiple sources, this method for DOI estimation is not consistent. Now, so there is a bias that does not tend to 0 when n tends to infinity, and this bias depends on how close the sources are and how different the powers of different sources are. I mean, this is quite intuitive. Now, remember, this is what we get when n, the number of snapshots, goes to infinity. But if you understood where the bias comes from, you can understand that we can conclude that the classical beamforming can provide, under some assumption, under some condition, can provide consistent estimate. Obviously, if the number of sensors goes to infinity, the array aperture increases, the resolution becomes better and better, and the interaction between different peaks tends to zero. But the problem is that we cannot increase the number of sensors because of the cost of the hardware. So for a fixed N, we can say that the classical beamformer is approximately a consistent method to estimate the K directional arrival if the sources are spaced enough. So what do I mean? If the DOR separation is larger than at least than the array beamwidth, which depends on the aperture. So if they are spaced enough, the bias can be negligible. Second assumption that makes the estimate good is that the signals are uncorrelated. So RS is diagonal. If they are correlated, the situation gets worse. And the third assumption is if the noise is partially white. So the contribution of the noise is a constant term. So it does not imply a shift, a change in the position of the peak. Under these three assumptions, if these three assumptions are satisfied, the classical beamformer, FFT based if we are talking about EULA, can provide accurate DOI estimates. So under this assumption. Otherwise, it is biased. So probably it's better to use something else. Now remember, the figure that I showed you before are for n that goes to infinity. In practice, we have to estimate the spatial power spectral density, and we use the n snapshot. So this is what we get, for example, if the noise power is 1, and we can collect 128 snapshots. So this is the average periodogram, the equivalent of the average periodogram that we get if we can average over 128 temporal snapshots. As you can see, the estimate is very good because this is very similar to this other one. What is it? It's pretty similar to this one. The position of the peak is the same. So N 128. Clearly, if the noise power increases, so the level of the white noise increases, basically you have a constant level that increases. So it starts, so imagine you have a constant level that goes up. So it starts to cover first the side lobes of the three sources. So you see the level increases, and it may cover, it may mask the weak source. So depending on the power of the noise level, the noise can mask the weakest sources. So first it masks the first source, which is the weakest, and then if it increases further, it can mask the other sources too. So this is the effect of white noise. And when you have to estimate the spatial power spectral density by using a given number of snapshots. Averaging over different snapshots allows to reduce the variance of the estimate. if you have only one snapshot, you calculate the periodogram and you plot the periodogram, but there is a huge variance. So you can get a very different result from one realization to the other. So this is one example, one realization, and this is another realization. So it's important that we average over different snapshots to reduce the variance in the estimate. This is a very general concept that is true almost always. Okay. We understood that one problem with linear array, and in particular EULA, but is true for any linear array, is that if you have a linear array, we cannot estimate separately azimuth and elevation. We can estimate only one of the two. So for example, we have to assume that the elevation is 0. So both the array and the sources are on the plane, and then you estimate the azimuth. If you want to, and this is fine if you want to estimate basically the direction arrival of a ship over the sea. But if you want to estimate the direction arrival of an airplane, for example, you have to estimate separately azimuth and elevation. And for this purpose, you can't use linear arrays. To estimate both elevation and azimuth, you need two-dimensional or three-dimensional array. I want to show you how we get the beam pattern in the case of two-dimensional array. Now, if you have a two-dimensional array, so the elements of the array distributed over a plane, the beam pattern depends on the elevation and the azimuth, and is defined as what? It is, so let's assume you have a signal that comes from a directional arrival specified by this elevation, phi t, and this azimuth, theta t. The beam pattern is what? Is the inner product between the array response and the impulse response of the beamformer. Now, if you use classical beamforming, H is the matched filter, so it has the same shape as the array response, and this is the beam pattern that you obtain when you steer the beam in direction, in azimuth, sorry, in elevation phi and azimuth theta. So basically, the definition of beam pattern is exactly the same. 1D, 2D, 3D, the definition is exactly the same. The structure of the array response is exactly the same, because a delay, if the signal is narrowband, is mapped into a phase shift, and the phase shift depends on the position of the elements in the array. So depending on the geometry of the array, you have a different expression of the position vector Rm. You have to calculate this inner product. You get the delay, you plug here, and you calculate the beam pattern. So it's very simple. So let's consider and compare three popular two-dimensional array structure. So the uniform circular array that is widely adopted in, for example, airborne radar, the uniform rectangular array, and the L-shaped array. Basically, the L-shaped array, as you can imagine, are two uniform linear array that are connected to form an L. So it's a planar array obtained by putting two Euler array, one vertical to the other. So let's consider, for example, the uniform circular array. Okay. So let's assume that the M sensors are distributed uniformly over a circle of radius r. And this circle is located in the XY plane. So we have the array in the XY plane. So the normal to the array is the Z axis, and the position of the M element in the array can be written in this way. The ascissa is R cosine of 2 pi over M that multiplies M minus 1. So when if M is equal to 1, you get cosine of 0, which is 1, sine of 0, which is 0. So the first element is in position R, 0, 0. And when M increases, you move over a circle, and the circle is located in the XY plane because the value of the Z component is always 0. So this is what is called uniform circular array. So you have the pointing vector, so the vector that points in the direction of propagation, that depends on elevation and azimuth. You have the vector Rm. You calculate the inner product between the two. The result is very simple, is this component multiplies this component plus this component multiplies this component. The third term is 0 because the array has 0 component along IZ. So this is the result of the inner product. You divide by the speed of propagation and you get the delay. And so in this way you can build the array response for a target that has elevation Pt and azimuth θ. So you get this, and then obviously A of phi theta has exactly the same structure. So you calculate the inner product. So you calculate this inner product, you take the modulo square, you divide by M square, and you have the power beam pattern. And for example, if you have a target with the elevation 45 degrees and azimuth 160 degrees, and the array is a uniform circular array with 36 elements, the separation, the distance between two of them obviously should be lower than lambda divided by 2 in order to avoid grating lobes. The radius of the circle has been taken equal to 3 lambda. So this is the value of the radius that, if the array has 36 elements, guarantees that the Nyquist criterion is satisfied. And so if you look at the two-dimensional beam pattern, phi is the elevation, theta is the azimuth, you see basically the main lobe at the right position, because you have 45 degrees elevation and 160 azimuth. It's not very clear from this picture, but believe me, the position of this peak is exactly in this directional arrival. If we use a different way to plot a 2D pattern, so if you use the color level plot. This is in linear scale, this is in dB scale. I mean, more or less, you see the same thing. So you can see that there is a main lobe at 45 elevation, 160 azimuth, and then you have all the main lobe structure all around. You can see in linear scale, you can see in dB scale. So you have the main lobe, and then you have the side lobe all around. So from this picture, you can see the size of the main lobe in azimuth and resolution. Now, it seems that, sorry, in azimuth and elevation. Now, apparently, it seems that the beam width is different in azimuth or in elevation, but this is due to the fact that the scale is different. This goes from 0 to 360. Instead, the elevation goes from 0 to 90 here. And so you have to calculate. If you want to compare with the other structure, well, okay, next break is 11:30, so we have some time. Okay, so now we want to compare the uniform circular array with the uniform rectangular array. So in order to make a fair comparison, let's assume that the number of sensors is the same, 36. And so let's assume that this rectangular array actually is a square array of size 6 by 6. So you have a square 6 by 6 with 36 elements. You can understand that with respect to an array where the 36 elements are distributed over a circle, here the aperture is smaller because you have elements also inside. And because the aperture is smaller, it's quite intuitive that the resolution is worse. So the main lobe is wider than in the other case. In fact, if you plot the two-dimensional beam pattern, you see that, okay, the peak is in the right values, but this main lobe is wider than in the previous case. And you can see that the main lobe is wider also from the color plot. So this is the main lobe, and it is wider than in this case. But if you look at the side lobe, the situation is certainly better because the side lobe are definitely smaller. You can see from, if you compare this picture with this picture. So you see here higher side lobes. So the uniform rectangular array, if you compare by assuming that they have the same number of sensors, as smaller aperture, so worse resolution, but better side lobes. So none is better than the other. They just have a different trade-off between resolution and side lobes. Now, if you look at the uniform L-shaped array, so again, we assume that we have 36 sensors. So basically, they are two uniform linear array, 18 along X, 18 along Y. In this case, clearly, because you have 18 along each direction, the aperture is greater than in the previous cases. So I expect the L-shaped array to have better resolution, but higher side lobe. Because if you compare with the same number of sensor, if it has better resolution, the price to be paid is in terms of side lobe. In fact, if you look at the two-dimensional beam pattern of the L-shaped array, you have a narrower main lobe, but higher side lobes. You have this ridge with very high side lobes. And you can see very well also from here. So you have very high side lobes with this structure, but a much narrower main lobe. So much better resolution at the cost of worse side lobe. So, I mean, if you compare these three structures, you can say the L-shaped array is the best from the point of view of resolution, but it is the worst from the point of view of side lobes. The URA array, uniform rectangular array, is the best in terms of side lobes, but the worst in terms of resolution. The uniform circular array is in between. Is not the best from neither from side lobe nor from resolution, but it's not even the worst. So, I mean, Yucca is among the three, is the one with the, we can say, most balanced beam pattern, because it has good resolution, even if not the best, and good side lobe, even if not the lowest side lobes. So this explains why it is widely adopted. It's a widely adopted 2D array because of this property. And it is used when you want to estimate not only the azimuth of a source, but also the elevation. Last 5 minutes. I mean, in this course, I will talk about spatial processing. So digital beamforming. Now, typically, you collect samples from different array elements. So you make a sampling in space, but then you sample also in time. And so what you collect is a space-time data cube. So your data are space-time. So the optimal processing should be two-dimensional space-time. And when it is adapted, we talk about space-time adaptive processing. But typically, two-dimensional processing has more computational complexity that the cascade of spatial processing and temporal processing. So to reduce computational complexity, most of the time you will see that in the receiver, the two kinds of processes are decoupled. First, we do spatial processing, so we steer the beam in some direction, and then we perform temporal processing on the signal coming from that direction. This way of processing is not optimal, but it has lowest computational complexity than two-dimensional space-time processing. That's why often you find temporal and spatial processing decoupled. And typically, I repeat, we perform first spatial processing, so we do beamforming, and then temporal processing. Temporal processing can be meshed filter or power spectral analysis or whatever. Sometimes to reduce the cost, if the number of elements of the array is very large, we don't digitalize the signal at the output of each element, but first we combine in analog manner a subset of them. So basically we build subarray. So we combine in an analogous manner the elements from that subarray, and then we sample only the output of each subarray. So we do digital beamforming at subarray level. This kind of schemes are called hybrid. Hybrid. So it is called hybrid in the sense that part of the beamforming is done in analog manner at each subarray level, and then part of the beamforming is done digitally by combining digitally the data that come from different subarray. Now, the choice of the subarray is various. You can have the architecture that is called regular. So all of them are equal. So the subarrays are composed by the same number of elements and maybe with no overlap. But in order to avoid the presence of grating lobes, typically we prefer to split the array in irregular subarrays. So the subarrays are different, and in particular can be made by a different number of elements. This is useful to avoid grating lobes. And then they can be non-overlapping or overlapping. And sometimes we tolerate a certain overlap because this allows basically to improve the performance of the processing. I don't have time to enter in these details, but this is what is typically done. Okay, I think we can stop here, and after the break, I will introduce you some numerical results, and I will pass you a MATLAB code, and I will invite you to use this code to check some results. So during the break, I will send the MATLAB code, I think, to Professor Badri if he's present.
Yes, sir.
Okay, see you in half an hour.